So with covalent bonds, remember that they give rise to all the molecular compounds, all the organics, the hydrocarbons and everything with carbon, all the functional group stuff, have covalent bonds for the most part in them. So there's a lot of molecules that have covalent bonds. And remember that in a covalent bond, the atoms are trying to get a noble gas configuration. They are trying to get usually an octet, usually 8 electrons. The one exception would be hydrogen. It only needs 2 because its first sublevel will be filled with 2 electrons. But to do that, they will share electrons between orbitals. And each atom, by doing this, each atom gains the use of that other partner's electron for its valence shell. So it's moving closer to that octet number. So this is a really nice visual. So the narrator is going to talk, so I'm going to be quiet while he does things.
Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen...
So I want you to notice as this is playing that the electrons kind of, 2 of them stay around hydrogen some of the time, but more often they're around oxygen because that's the electronegativity showing. Sometimes they'll go around hydrogen, but more often than not, you'll see them around oxygen.
And hydrogen atoms collide. Covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
So last year we spent a lot of time talking about the fact that oxygen is pulling hydrogen's electron more towards it, but it's still in its orbital. That's not true all the time. You notice that it's flying around oxygen, it flies around hydrogen, and so on and so forth. So that's really more of a realistic picture of what's going on. There's constant movement going on. But the fact that a pair of electrons are moving back and forth between hydrogen and oxygen is what's really keeping them together. So types of covalent bonds, we can use electronegativity to figure that out. Knowing what the electronegativity difference between the 2 atoms lets us know this. This is called the Pauling set of electronegativities. It's what we use in class. It's what is in the appendices that you have with you on Schoology and so forth. Fluorine given the 4.0 as the highest electronegativity. Notice the halogens aren't here because they don't want to pull electrons in. There's no need for them to pull electrons in. So using these numbers is going to help us decide whether or not you're going to get a polar or a nonpolar covalent bond. So if you have an electronegativity difference that's between 0 and 0.4, we're going to call that a nonpolar covalent bond. That means the atoms are being shared pretty equally between the 2 electrons. So they're moving back and forth to spend 50% of their time at one atom, basically 50% of the time at the other atom. With a polar covalent bond, now we've got electronegativity difference of 0.5 or greater, which is what you saw with hydrogen and oxygen. Oxygen is 3.5, hydrogen's 2.1, so you have well over a value of 1 for the electronegativity difference. So that means that oxygen is pulling the electrons strongly, and the electron doesn't spend as much time around hydrogen as it does around oxygen. So we you learned last year about Lewis or electron dot structures. So we're going to review those in order to be able to kind of start drawing structures. You only show the valence electrons. Each dot represents one of those valence electrons. We put the dots around all four sides of the symbol. The number of bonds an atom's going to form is typically determined by the number of electrons which are not paired. That's a really good rule of thumb. You're going to see a bunch of different rules in the textbook, but a good rule of thumb is if the electron is unpaired, it's going to try and form a bond. So here you've got sodium forming 1, magnesium forming 2, aluminum forming 3, silicon forming 4. But now that we have a pair, phosphorus is back down to 3, sulfur is back down to 2, chlorine's down to 1, and argon nothing because it's got a full octet. So when you draw the Lewis structure of an atom, you can predict how many bonds they are going to form. So valence electrons are what are distributed and shared when you have covalent bonds forming. So there are bonded pairs and there are non-bonding pairs, bonding pairs and non-bonding pairs. So the bonding pairs we show as a line, non-bonding pairs in a Lewis structure we show as a pair of dots. Okay, so Lewis structures show all the valence electrons, bonding and non-bonding. So it's important to remember that you've got to show all those non-bonding pairs of electrons. When you have bond formation, basically what you have going on is you have an overlap of two orbitals. And so the electron from hydrogen can overlap with the electron, or the orbital from hydrogen can overlap with the orbital from chlorine, and then the two electrons will be shared. And obviously for them to occupy the same space, they're going to have different spins. So sometimes the electrons actually need to change their spin in order to form a bond. So talking about bond polarity is kind of the natural next step. So two electrons shared between two atoms form a covalent bond. If those electrons are shared equally, we have a nonpolar covalent bond, or nearly equally. You'll have other people argue with that fact. You will have some people say that unless the electronegativity is actually 0, it's a polar covalent bond. We're going to not go with that idea. If one atom has a stronger attraction to the electrons, you're going to get a polar covalent bond. And as a result, you wind up with a polar bond. If you have a complete transfer, which is what happens in an ionic bond, you are going to see a cation and an anion form. In a polar molecule, there are no cations and anions, there are just partial charges. But in ionic compounds, you have true cations and anions. All ionic compounds are considered polar because of that fact. So here's a nice visual of bond polarity. So if you have something where the polar bonds are very similar, the green represents an even distribution of electron density. But as you start to get into differences in electronegativity, for example, this is H and F, hydrogen is losing some of the electron density, whereas fluorine is gaining it. So the red means high electron density. The blue means lower electron density. So notice that hydrogen has more negative ideas, more electron density here, but hydrogen still has a reasonable amount. When you get to LiF, which is ionic, now you have almost all the electron density being near fluorine and essentially nothing being around lithium. So the more red you wind up having, the less blue you wind up having. And so the blue is low electron density, the red is high electron density. So bond polarity causes what we refer to as dipole moments. And this is actually the quantitative measure of bond polarity. We never really looked at that in first year. We're going to look at it a little bit in this year. Not going to calculate it too much, but just know that the things that contribute to a bond dipole are the differences in electronegativities, the length of the bond. So this is something that we have not looked at before. We haven't looked at bond length before. And so we can generally use the change in electronegativity to get a qualitative sense of bond polarity, but we've got to think about the bond length in order to understand how bond polarity truly is generated in terms of the dipole moment, the quantitative stuff. So we give bond dipole moment this is the Greek letter mu. So you've seen it for micro, but now we're also using it for bond dipole moments. So the bond dipole is equal to the charge times the distance. So you're looking similar ideas to Coulomb's law, which makes sense. We're, opposite charges attracting or the distance between them and so forth. But the dipole moment is increased with an increasing radius. So keep that in mind. The farther apart the atoms are, the more dipole moment you have. So that's the opposite of Coulomb's law. Before it was the closer they are, the stronger it is, the further apart they are, the weaker it is. In this case, both of them positively impact the dipole moment, the distance between the ions and the charges of the ions themselves, or the electronegativity values, I should say. So large dipole moment obviously means that you have a more polar molecule. So here's an example, really good visual of the halogens bonding with hydrogen. So fluorine has a very large electronegativity. 4.0, hydrogen's 2.1, so the difference is 1.9. Huge difference in electronegativity. Bond length is small, but the dipole moment winds up being, you multiply those two together, the dipole moment winds up being 1.82. Okay, so HCl, dipole moment is decreasing. Notice what happens as we go from HF, lot of red, little red, no red, almost all green, because look at the difference between electronegativities is 0.4. So you almost have a pure covalent bond. Little bit of leaning to one side, but by looking at this, what can you conclude has a larger impact on the dipole moment, the bond length or the electronegativity? Hopefully you're seeing that it's the electronegativity that has a much bigger impact on the dipole moment. Okay, so bond length is one last thing that we want to talk about. Bond length is the distance between the nuclei. And so the distance between bonded atoms is going to decrease as you increase the number of bonded pairs of electrons. So the other thing about bond length you need to remember is that a single bond is the longest, triple bond is the shortest. That's going to come into play a lot as we get into three-dimensional shapes of molecules. So next up, we will go into drawing Lewis structures for molecules. We've drawn Lewis structures for atoms, but we're going to get into Lewis structures for molecules next.